do a warm-up on that, and then I'll do another example from 11.3, and then basically we'll be done with 11.3. All right, let me let you copy this down. Okay, so we want to use implicit differentiation, something you learned in Calculus 1, to find these two partial derivatives. Of course, now what you're doing is you're finding partial derivatives. So, of course, as you learned, we have to differentiate. If we focus here on the partial derivative of z with respect to x, well, all right, what do we have to differentiate both sides of the equation with respect to? What variable would we differentiate both sides of this equation with respect to? If we're looking for this partial derivative, that's right, Eric, x. And z is implicitly, by the way, z is understood implicitly to be a function, based on this equation, z is implicitly understood to be a function of what variables? Good, x and y. Think about it. If you change x and you change y, you'll get a new value of z, right? And or a different value of z. So we're looking for the rates at which z varies with respect to x and the rate at which z varies with respect to y. But we're going to start off by differentiating both sides of that equation with respect to x. And so, here's the setup. All right, and this is the kind of work I would want to see on the exam, right? Nice, complete work. Differentiate both sides of the equation with respect to x. Now on the right side here, we get 1 over 1 plus yz quantity squared times the partial derivative of x of yz. So what rule did we use for the right-hand side there? What rule is that we're applying? Good, Robin, the chain rule. We use the chain rule here. Absolutely. All right, and now I'm going to take the partial derivative of y, the product function yz with respect to x, So I use the product rule. I'm holding y constant. I'm holding the y constant. Okay. Right. And so this is my result using the what rule did I use here in calculus? Good, Robin, the product rule. Okay. And so, you just do what you need to do here. And of course, we want to isolate the partial of z with respect to x, that partial derivative. So we can factor that out on the right-hand side here. We can factor that partial derivative on the right-hand side. That's going to give us this, and then we'll divide both sides by this expression. That'll get us here, and then we simplify a little bit. We can multiply, let's see, we can multiply top and bottom. Let me see here. Oh, yeah. Hold on. I want to make that a little easier. So I'm multiplying through top and bottom by 1 plus y squared z squared on the top and the bottom. Just gets it in a nicer form, and that's also helpful in WebAssign. Easier to type, right? And this is going to be then your answer, equals this is going to be your answer. All right, let me know if you have any questions down to here. All right. Now we need to get the other partial derivative. May I go to the next page? All right, Christopher's good. All right. All right, well, let's go to the next page then, if we're good. Yeah, here's that factoring step, right there. Okay, next page. Now I find the partial derivative with respect to y, so I differentiate both sides with respect to y. And I'm going to hold the x constant now. And so the partial derivative of x with respect to y is 0. And again, I'm using the chain rule and the product rule. And if you work it out, you're going to get this as your answer. Partial derivative of z with respect to y will equal negative the fraction z over y plus 1 plus y squared z squared. It's really quite beautiful. All right, are there any questions? Are there any questions? Very good. Are we ready to go to the next example? All right. All right, very good. So, okay. All right, here's a new one. Here's a new one. New example. Let me give you a moment to copy this example down. Okay, so let's take a look at this. All right, we have a paraboloid. A paraboloid. We know what a paraboloid looks like. Incidentally, is this paraboloid is it a sideways paraboloid? Or, I mean, I guess what I'm asking is, does this paraboloid open upward, downward, sideways? How does this paraboloid here open based on the equation? Good. It opens, good, Eric. It opens downward. This paraboloid opens downward. That's right. And what axis goes through this paraboloid? What axis goes through the paraboloid? Well, I guess it'd have to be the z, right? Okay, good, good. We have some students here. Okay, it'd have to be the z-axis. All right, that's fine. And I'm curious, what's this point right here? So, you know, the paraboloid don't open, it keeps going down, right? Okay, that's right. Good, Ryan. Good, Eric. It's going to be 0, 0, and 6. Now, what we're going to do is we're going to take this paraboloid and we're going to cut it with the plane x equals 1. So is x equals 1 a horizontal plane or a vertical plane? It always helps to get a little feel. I mean, they're saying it intersects the plane in a parabola. That's right, Chris. That's right, Robin. X equals 1 is a vertical plane that intersects the x-axis at x equals 1. And it's gonna cut this parabola. The cut of the parabola is going to be the cut of the paraboloid. When this plane cuts the paraboloid, the cut is going to be a parabola. The cut is going to be a parabola. So there is a parabola. You know, sometimes these word problems, how many feel kind of uncomfortable when they get to a word problem like this? Or a little bit nervous? Traditionally, students are a little nervous when it comes to word problems. But you know, if you just kind of take it slow a little bit, think about it, you can piece together what they're looking for. So, all right, this plane cuts the paraboloid. The cut is the cut is going to be a parabola, and we want to find parametric equations for the tangent line to this parabola at the point 1, 2, -4. Okay. Now is 1, 2, -4 on the paraboloid? Is this point on the paraboloid? I mean, should it be on the paraboloid? I mean, they just came up with this point 1, 2, -4. But I'm asking, is that point on the paraboloid? That's right, Ryan. It is on the paraboloid. And that makes sense because the plane cuts the paraboloid in the parabola. But the parabola has to obey the equation of the paraboloid because it's on the paraboloid, right? So we want to find the tangent line of this parabola at the point 1, 2, negative 4. Equations of a tangent line. Okay. So let's go ahead to the solution here and see how to do this problem. All right. So first of all, what I do here, I have a nice picture. I have a nice picture where I have the plane x equals 1. Okay, you see it cuts the x-axis right here at x equals 1, and it's going to cut the paraboloid, therefore giving this this parabola. And the point 1, 2, negative 4, what I did was just to kind of give a little perspective. I moved out along the x-axis 1 unit, and then I moved in the direction of the y positive 2 units, and then I moved down 4 units, and that got me to the coordinate. That got me to the coordinate 1, 2, negative 4, right there. Okay, that's the maybe I'll put it in black. That's the point that I'm at, and there is a tangent that's on the parabola, and I'm interested in this. I drew this tangent line, this nice big tangent line. Hold on. I drew it, and I want to find parametric equations for that. Okay, so well, tangent line, for some reason, okay, we know that to get a tangent line, we need to take a derivative. We know that. But for some reason, I'm taking the partial derivative of z with respect to y. Okay, remember z was the equation of the, hold on here, of the paraboloid, which was 6 minus x squared minus 2y squared. Now, I could have taken the partial derivative of z with respect to x or y, but I chose to do the partial derivative of z with respect to y, the y variable. Okay, so that means I'm holding x constant, and I'm trying to find how the surface changes. Hold on, yeah. Hold the x constant. What is the rate of change of the surface with respect to y? As y changes, how does the surface change? So does it make sense based on the picture that I would want the partial derivative of z with respect to y? Based on that blue tangent line to the parabola at 1, 2, negative 4. Okay, thank you, Ryan. Yeah, I'm hoping it makes sense. So the slope, the tangent line, the height of the tangent line changes with respect to y because x is being held constant. That tangent line is x coordinates are always equal to 1 for that tangent line. So z changes with respect to y. So what I do then is I get the partial derivative of z with respect to y, and then I evaluate that for when x is 1 and y is 2. That's going to get me -8. But what does that mean? Well, I write -8 as -8 over 1. And so I think of that then as for a rise of -8 units in the z direction. Well, no, let's think of it like this. If I run one positive unit in the y direction, I'm going to rise -8 units in the z direction. And that means the line is going down because the slope's negative. And sure enough, this line is going down. And so therefore, here are my parametric equations of the line. Notice the 1, 2, and -4. Now that's just a point on that line. That's just this point right here. But then the slope, well, if for every, I mean, think of the vector 0, 1, and -8. Think of that vector. That vector is, hold on here, let me be a little bit careful. That vector is 0, 1, -8. Is pointing in the same direction as the tangent line. Pointing in the same direction as the tangent line. And so components are, the direction numbers are 0, 1, -8. And again, it has to do, this whole thing is based on the right interpretation. What does this partial derivative of z with respect to y mean? It means that if you move one positive unit in the y direction, you'll go down 8 units in the z direction. And that is the right, that makes sense based on the graph, and just based on the problem itself. Okay, and I made a little aside here, just how did I get this 4004 here? Well, if x equals 1, which it is for that parabola, then the largest value of the paraboloid, probably should say parabola, not paraboloid, parabola. The largest value of the parabola would be 004. You know what I mean. You know what I mean. It's you know what I mean. Okay. So these are a few. This is just a little bit deeper problem, in the sense you're trying to understand what derivatives mean, what the partial derivatives mean, and you'll have in section 11.3. It's only 2 exercises, but you'll have a problem like this, and you'll have a problem that deals with hey, what is the derivative mean? And maybe there are 3 questions on that. I'll double check. But are there any questions so far? Okay, I'll stop the recording.